Good morning. Am I audible? Okay, Abhi. So we continue. We have seen in the previous lecture advantages of Nfnl or Nfa. Now we look at converting Nfnl to an Nfa. Any Nfnl can be converted into an equivalent Nfa. When we say equivalent, it means both of them accept the same language. We can convert any Nfa to DFA. That is our theorem 4.1. Non-determinism does not add power, which means whatever possible using non-deterministic finite automata, it is always possible using deterministic finite automata in terms of language acceptance. So converting Nfnl to Nfa, if you just recollect, we had seen delta star, definition of delta star in the previous lecture. Delta star for Nfnl, the definition, and then we worked out an example. Now, the claim is we can convert any Nfnl to equivalent Nfa. That is a theorem, theorem 4.2. We'll do that later. Right now we work out the examples, how we convert Nfnl to an Nfa. Once again, this conversion is based on the theorem. Just to make the things easier when we discuss theorem, we are going in the reverse direction. Looking at the example, which is based on the concept in the theorem, and then we'll look at the proof. So converting Nfnl to Nfa, the language is 0 star 1 0 1 star 0. We have drawn Nfnl 0 star. So in state number A, we put a loop 0 star. Then we have 0 1 star. So there's a concatenation, and whenever there's a concatenation, we put a null transition. So we have 3 blocks. One is for 0 star, another is for 0 1 star, that is between states B and C. Ending with 0, the last part, that is 0. In fact, that is 0 star. So in the state D, that is in the state D, we have minute. The last part is 0 star. That star is not visible. So in the state D, we have a loop on transition 0. So language is 0 star, 0 1 star, 0 star. We have plotted Nfnl 0 star in the state A, null transition. Then we have between B and C 0 1 star, and one more null transition because it is dot 0 star, the last part of the RE. And so in the state D, it is 0. D is the accepting state. Now, the states in Nfnl. Now, when we convert Nfnl to Nfa, number of states remain same. That is rule number 1. When we convert Nfa to Fa or DFA, there is increase in number of states, and that number of states depends upon number of subsets. And we have states that are reachable from the initial state. So only we keep that many subsets or states. Only we keep track of the reachable states from the initial state. So we don't take all the subsets, but we only consider reachable states from the initial state. No point in considering states that are not reachable from the initial state. So here, when we convert Nfnl to Nfa, a very simple thing is number of states does not change. So basically we want to remove those null transitions. Number of states does not change. So in the row, number of rows, that equals number of states. So we'll see the first column Q. The states are ABCD. Sorry. The states are ABCD, same number of states in Nfnl, Nfa. And based on this our state transition diagram, Normally that will be given, that is an input. A state transition diagram will be given. Just for the sake of understanding, for the language 0 star, 01 star, 0 star, we constructed Nfnl. Usually that will be given as an input. So from the diagram, we write delta Q null, delta Q0, delta Q1. So we have transition defined on 0 from a state, defined on 1, and also we have defined a transition on null because this is Nfnl. So the columns are delta Q null, delta Q0, delta Q1, second, third, fourth column respectively. And these columns are filled based on our input Nfnl. So delta Q null for the state A on null, it is B. So the first entry is B. Delta Q null. Delta Q0 for the row A, that is delta A0, it is A, that is A, and on 1, that is 5. That is 5. Similarly, B on null, it is D, B on 0 is C, B on 1 not defined, that is 5. C on null, that is 5, C on 0 is also 5, C on 1 it is B, and D on null is 5, D on 0 is D, D on 1 is 5. This row A, for row A, delta Q0 it is only A. I think that is seems like B, but it is not B. It's only A. A on 0 is only A. We are writing transitions for 0 only. So that is A. That is not something just it looks like B or C, but it's only A. Fine. So we have from the state transition diagram, we have filled those rows, those columns 1, 2, 3. Q is ABCD, and then we have filled delta Q null, delta Q0, delta Q1. Next 3 columns based on the state transition diagram. Last 2 parts that are important actually. The most important here are last 2 columns because we are constructing NFA. So we are removing null transitions. We need to capture the impact of null transitions, and it is captured. We now know it is in the definition of delta star. So that is delta star Q0, delta star Q1, because we won't have transition defined on null when we convert Nfnl to NFA. So delta star Q0, delta star Q1, here we compute, and in the computation, it is our definition of delta star, which is in terms of null closure. Definition of delta star, we know, we had worked out example earlier. This one. This delta star computation. Delta star Q010 we had worked out. And it is in terms of null closure. So similarly here, we need to fill up last 2 columns. And that is delta star Q0, delta star Q1. It is based on the definition of null closure. Fine. Now, A on 0. In this example, I mean, this is based on the definition of our delta star for Nfnl. Now, computing delta A0, the same impact we are capturing directly. For example, let's see. Last 2 columns are important. First is our state Q. Next 3 columns are delta Q null, delta Q0, delta Q1 based on our state transition diagram. So we don't need to think much. Now we compute delta star Q0, delta star Q1. Actually, it is based on the null closure used in delta star definition. However, we can also compute that directly. Let's see. A on 0, delta star A0, answer is A. A on 0, answer is A. Using null transition, we can go to B. Using null transition, we can go to D. So A, B, D straight away will come. We are computing delta star A0. So A0, A on 0 is A itself. We take A on 0 A, then take a null transition to B. So answer will also be B. From B, we take a null transition to D. So answer will be A, B, D to begin with. Consume 0 in the state A because 0 is already consumed. Now I don't have any symbol. So only null transitions are to B and from B to D. So answer is A, B, D to begin with. Alternatively, we don't consume 0, yet it is not consumed. We reach state B, A null B, we go to B. 0 is not consumed. And then we consume 0 and go to C. So delta star A0 will also include C. It is delta star A0, so A must be consumed. So either we consume A in the state A itself, A0A, 0 is consumed. So answer is A. On null, no symbol required, so we can go to B. On null, we can go to D. So ABD will come as it is. Otherwise, we go from A to B on null, nothing is consumed. B to C on 0, so 0 is consumed now. So answer will be C. So answer is A, B, C, D. Delta star A0 is A, B, C, D. Delta star A1, that is fine, it's not defined. Is this fine? Delta star A0 is A, B, C, D. Is that fine? Any doubt to anyone? That is the most important in converting Nfnl to Nfa. This we are working directly. Actually, these computations will be based on our definition of delta star. Those computations, when we program it, it will be based, of course, based on our definition. The same definition we are using in this direct calculation. Is that fine? Keval, Dev, Abhi, Munaf, okay. Now we continue. Delta star A0 and A1, or delta star B0 and B1, that is next row. The same line. B0, delta star B0. Focus on last two columns. Delta star B0. So B0, B on 0, we can go to C. One of the answers is C. Or maybe we go to D, D to null D. So far we have not consumed 0. So answer won't be D yet. But then we consume 0 in the state D. Now 0 is consumed. Now D will come. So answer is C, comma D. Answer is C, comma D. And delta star B1, answer is 5, no transition defined. So it is C, comma D and 5 for the row B. For the row C, delta star C0, C0 not defined, so that is 5. C on 1, answer is B. And after consuming 1, still we can go to D by null transition. So D will also be included. Had there been B to D on 1, then D won't come because C on 1 it is B. Suppose instead of this null, B to D on null, it were B to D on 1, then D would not have been there. Because we are computing for 1 only, not double 1. 1 null is equal to 1, but 1, 1, that is a different string. So C on 1, answer is B, and because there is a null transition, D will also be included. So it is B, comma D. And lastly, D, it is simple, D0 is the 1 not defined. So there is my delta star Q0, delta star Q1. Is it fine? These computations so far? Keval, I am getting feedback. Abhi, Dev. Okay. Row B, fourth column. Which one is B? B, okay. Row B, fourth column. So delta, let's see, delta star B0. D on 0, we can go to C, so answer is C. Now from C, there is no null transition defined, so far only answer is C. B on 0, answer is C. And from C, on null, nothing is defined, so no more addition because of this particular transition. However, we can go to B to D on null. So we are computing B from B on 0. So we are exploring alternate path. So B on null it is D. So yet we have not consumed 0. So nothing added. So far D we won't come. But D on 0 is D itself. Now we are consuming 0. So it is something like null, then 0, and then to the state D. Therefore, D will be included. Social, therefore, D will also be included. Okay, fine. So these are last two columns. These are last two columns. And then it's very easy to construct. I mean, this is NF. This itself is last two columns. That is my NFA. We represent that pictorially. And this is my state transition diagram. Same number of states. ABCD. Converting Nfnl. This is my Nfnl. Getting NFA. Table we have constructed. Now we are representing that as a diagram. So same number of states A, B, C, D. Don't worry about the accepting state as of now. My initial state was A, remains A. Initial state was A, that remains A. Same structure, same number of states. Only difference are addition of the transitions. For example, A on 0, it is A, B, C, D. So you will see here, A on 0, it is A, B, A on 0, C, A on 0, the bottom link to D. A on 0 is A, B, C, D. So A on 0 is A itself, then it is B, also C, and this bottom link A to D on 0, that is A, B, C, D. So we need to add these transitions only. Same number of states, same structure, except addition of links. So for example, B on 0 is CD. So B on 0, there is a transition to C, there is a transition to D. C on 1, it is BD. C on 1, so C to B on 1, and C to D on 1. C on 1, it is BD. So this is my state transition diagram. Alternatively, I mean, fine, we can have this table and we define the initial state, that is A, and also define the accepting states. Here only changes, D was accepting state in my input Nfnl, remains accepting state in NFA. So that is D. Moreover, because we can reach to this accepting state D on null, say A to null, A to B on null, B to D on null. So A null B, B null D. So we can reach to the accepting state from the initial state without consuming a symbol, that is on null. Therefore, additionally, the initial state is also made an accepting state in this particular case here. So apart from D, we have added this state A. In case we are able to reach an accepting state from the initial state, if we are able to reach any accepting state from the initial state using null transitions only, then we make the initial state as an accepting state. This is based on our definition of this. When we convert Nfnl to Nfa, the theorem, that is our concept in the theorem. If we are able to reach any accepting state from the initial state using null transitions only, then we make the initial state as an accepting state. That we did. So this is my Nfnl, the state transition diagram for Nfnl. We could have only state transition table, put A arrow before A, put double circles over A and D being accepting states, or circle over A and D being accepting states. That is also fine. However, possible, if time permits, better go for the diagram. That will make the things more clearer, visually better than a table. So this is my NFA for given Nfnl. So we have converted Nfnl into NFA, and this is my state transition diagram for 0 star, 0, 1 star, 0 star. Is that clear? Is that fine? Prince, Cable, Devans, Abhi, Munaf. Okay, let's see. I think it will be next example. Okay, now we just for practice we convert this NFA to DFA. Let's convert this. We started with Nfnl and we got equivalent NFA. This is my equivalent NFA, and we know how to convert NFA to DFA. So just for practice, we convert this into a DFA. When we convert any NFA, again, here in this NFA, last two columns are important. Even if we remove this first, second, third, that's fine. Still that works, because the capture of to capture the null transition effect, last two columns are important, and based on that, we have converted that into NFA. So now we convert this NFA into DFA, deterministic finite automata, and we know converting NFA to DFA, we copy row number 1. So here it is. A, B, C, D, phi. Only look at the leftmost column, that is Q, and the rightmost two columns, delta star Q0, delta star Q1. When we convert NFA to DFA, it's easier if we look at the table. So we are looking at the table. We are looking at the leftmost column and two rightmost columns. So A, B, C, D, phi. And we convert NFA to DFA, we copy row number 1. So that is what we have done. Subset construction algorithm. One more example we are working. For the practice, we are converting this NFA to DFA. Otherwise, it was only converting Nfnl to NFA. It is over at this point. Just to take it further and apply our subset construction algorithm, we are converting this NFA to DFA. So those column titles, subset S, delta S0, delta S1, that is my, those are my column titles. We copy row number 1. So it is A, B, C, D, phi. From the table, we look at the table. A, B, C, D, phi. Leftmost column, rightmost two columns. So we have already encountered 3 subsets now. Those are my states 1, 2, 3. A, B, C, D, phi. 3 subsets we have encountered. For every unique subset, there is a unique state in the equivalent DFA. So for the subset A, we have 1, next subset 2, next subset 3. And we may take subset 2, A, B, C, D. So 2 on 0 and 2 on 1. Let's see. It is A, B, C, D on 0. So it is a second rightmost column, delta star A0. A, B, C, D on 0. So it is the second column from right. And it is union. We know that. We have already worked out few examples. So it is union of ABCD, CD, phi, D. Answer we know, that is ABCD. And in the next case, the rightmost column, ABCD on 1. So that is union of phi, BD, phi. So answer is BD. So that is, those are entries in row number 2. ABCD on 0, it is ABCD. On 1, it is BD. ABCD is already encountered. Label that we have assigned is 2. So that is state number 2. For BD, we have assigned label 4 because till now we have assigned label 3. 3 subsets have been encountered. This is a new subset, new label. Any label can be given. You can label this as BD itself. That is fine. I prefer 1, 2, 3, 4. So that is my label 4, state number 4. Next is state number 3, label 3, phi. Whenever there is phi, you can blindly write phi, phi, phi. Phi, phi, phi. So that is 3 on 0 is 3, on 1 it is 3. So that is phi, phi, phi. Fourth is BD. Fourth is BD. So BD on 0 and 1. BD on 0 and 1. Rightmost two columns. So it is CD, union D. So that is CD, yeah. Cable that is fine. CD and phi. Correct. DD on 0. So that is CD union D. The answer is CD. Phi union phi, that is phi. So answer is CD and phi. That is CD and phi. CD is not yet encountered. That is a new subset, new state, new label. There is number 5. The phi label is 3 already given. We continue and take CD. CD on 0 and 1. CD on 0 and 1, it is D, BD. CD on 0 and 1. So it is phi union D, answer is D. Is BD union phi, answer is BD. So the answer is D and BD for 0 and 1 respectively. So answer is D and BD for 0 and 1 respectively. D is a new subset, so label number 6. DD already encountered, label 4. Going further, it is D, and D, it is D and 5 we know. The last entry, D on 0 is D, on 1 it is 5. So answer is D and 5. D is our label number 6, 5 is our label number 3. So that completes transitions for all unique states, all reachable states from the initial state. Now there is no more reachable state. So it is 1, 2, 3, 4, 5, 6. Or whatever label you want to give, I have given 1, 2, 3, 4, 5, 6. You may give it label as name of the subset itself, something like A, B, C, D, phi, B, D, C, D, T. So that something which is there in red, those labels are name of the subset itself. A, B, C, D, phi, B, D, C, D, D, whichever way you want. Transitions we know. Transitions we know. A on 0 or 1 on 0 is 2 and on 1 it is 3. So those are transitions. A on 0 it is 2, A on 1 it is 3. Similarly, we take say label 6. 6 on 0 is 6, on 1 it is 3. So 6 on 0 is itself, and on 1 it is 3. Similarly, transitions for all remaining states. For example, from 5 on 0 is 6, and 1 it is 4. 5 it is 6, 4. So 5 on 0 it is 6, 5 on 1 it is 4. So we have defined these transitions. My initial state is the subset corresponding to the initial state corresponding to the initial subset, that is A. So my initial state is label 1. That is my label 1. Now accepting states in my this input NFA, accepting states are A and D. So any subset in which A or D is present becomes an accepting state in the equivalent DFA. So we look at A and D, presence of A and D. So A is present in 1, A is present in 2, it is not present in 3, E is present in 4, and D is also present in 5, E is present in 6. So except number 3 label, remaining all are accepting states, except 3. And 3 is 5, we know once it is 5, we don't come out from that, 5, 5, 5. Once we reach state number 3 corresponding to 5, we don't come out from that. So that is a dead state. So except label 3, remaining all are accepting states, and this is my equivalent DFA for the given language. 0 star, 0 1 star, 0 star. This is my equivalent DFA. See, again from this DFA you can see 0 star, 0 1 star, 0 star. This is my DFA, and how easier was our Nfnl. This was my Nfnl. 0 star, 0 1 star, 0 star. How much easier was it to construct Nfnl for the language 0 star, 0 1 star, 0 star. This was my DFA, which is easier to construct compared to DFA. This is my NFA. The easiest thing to construct is our Nfnl for a given language. Fine. So we have converted Nfnl to NFA, and also we worked out to convert that into DFA from NFA. Is that fine, students? Keval, it is fine to Keval, Dev, Abhi. Munaf, fine. So basically we were discussing how to convert Nfnl to Nfa, and that is based on our theorem 4.2. One example we have worked out converting Nfnl to Nfa. Let's see if we can do the second example. Another example for converting Nfnl to Nfa. Here is my input Nfnl. Example number 2. Converting Nfnl to Nfa. In the language is 0 star, then 0 1 star, then 1 union 0 star 1 star 0. That is my example number 2. Another example for converting Nfnl to Nfa. Again, let us look at this language 0 star. Let us go in the reverse direction. Suppose we want to convert this RE, we want to construct Nfnl for the given RE, then start with my state A, which is initial state, then there is a 0 star, so there is a loop in the state A, then 0 1 star, it is a concatenation, 0 star dot 0 1 star, so concatenation means take null. Then we have 0 1 star, so between B and C there is a loop with the symbol 0 1, 0 1 star, loop between B and C, B to C 0, C to B 1, and then again this is a loop 0 1 star, this dot that is ending with 1. So here between B and E we have taken 1. Between B and E we have taken, in the optimized we can remove, when we optimize given Nfnl we can remove extra null transitions. So we have not put here null transition. We'll discuss this further when we talk about what is called Klein's theorem, the next topic. So B to E, that is 1. 0 star, null, then it is 0 1 star between B and C, then ending with 1. So B to E, that is 1. Union, whenever there is a union, we take null transitions. From the initial state, whenever there is union, we take null transition. The upper path, A, B, C, E, that is for the language 0 star, 0 1 star 1. The lower branch is for the language A, D, E. Once again, it is 0 star, that is A itself, that is 0 star. Then 1 star, that is in the D state, and then 0. So 0 star, 1 star, 0. Little printing mistake in the textbook, if you are referring to, should be referring to your textbook. That 0 part is missing. 0 star is missing, it is not printed. It has to be there. 0 star has to be there. As per the printing mistake in the textbook, it is only showing 1 star 0. Actually, it is 0 star 1 star 0. So that example is 0 1 0, the string 0 1 0. So we can't omit that 0 stars. Otherwise 0 1 0, 0 1 0 won't be accepted. 0 1 0 won't be accepted. See 0, that is state A. Then in the state D, that is 1. And then in the state E, 0 1 0. That is accepted by this Nfnl. And if you don't write that 0 star, then we can't accept 0 1 0, which is accepted by this Nfa, but it is not part of the language. 0 1 0. 0 1 0 you can't get from the RE. If you don't write after union this 0 star, we can't get 0 1 0. It is compulsory to write 0 star. Otherwise also it is visible in the state A. There is a loop, that is 0 star. So 0 star 1 0. Fine. It's a small printing mistake, that's it. So this is my Nfnl, which is input. We want to convert this Nfnl to Nfa. Language is 0 star 0 1 star 1 union 0 star 1 star 0. That is the language. And here is my equivalent Nfa. Again, states converting Nfnl to Nfa, same number of states. In my input Nfa, we have 5 states, therefore 5 rows, A, B, C, D. No change in the rows number when we convert Nfnl to Nfa. When we convert Nfa to DFA, number of rows increases, number of subsets increases, number of states increases, number of rows increases. So 5 rows. From the diagram, state transition diagram, we fill up first 3 columns. I mean, apart from Q, we fill up next 3 columns: delta Q null, delta Q0, delta Q1. So let's see. Let us take A on 0. Okay, first is A on null. A on null, answer is BD. A on null, answer is BD. A on 0, only A. A on 1, it is 5. So that is my next 3 columns: delta Q null, delta Q0, delta Q1 for the state A. Similarly for B, on null, not defined, that is 5. B on 0 is C. B on 1, that is E. We are not looking at rightmost 2 columns right now, only considering column 2, 3, 4. My column 1 is Q. Column 2, 3, 4 we are taking. So C. C on null, that is 5. C on 0, not defined, that is 5. C on 1, it is B. E. D on null, that is 5. D on 0 is E. D on 1 is D. And E, it is null, 0 and 1. For everything, it is 5. No transition defined. So E is 5, 5, 5. So those are columns: delta Q null, delta Q0, delta Q1. Actually, when we apply this formula, we require these columns. Incidentally, we use the state approach and we directly computed these values. Delta star Q0, delta star Q1. But actually, when we apply this formula, delta star, we need these values. Therefore, we are writing delta Q null, delta Q0, delta Q1. Delta star Q0, delta star Q1. Again, that is based on the formula. To compute that, we require the content of delta Q null, delta Q0, delta Q1. Fine. But when we directly compute, actually indirectly it is based on the those definition only. But there we don't require the content of the second column, third column, fourth column. For the sake of completion, when assuming that we'll be using formula, we are writing it. Fine. Now we take the straight approach. Delta star Q A0, delta star A1. Find out delta star A0 and A1. Compute that. Find out delta star A0, delta star A1 for this Nfnl. Find out that. Calculate yourself. What should be delta star A0? Find it out. Keval is asking me why there is no null transition from state B. That's what I said, no? Concatenation we can achieve exactly if we follow the theorem, then we achieve that using null transition. But we can optimize that and remove unnecessary null transition. We'll discuss this further when we discuss the next topic, that is Klein's theorem. This, yeah. Tell me delta star A0. Keval is saying A, B, C, D, E. Okay, correct. Dev, what are you saying? I didn't get. Yeah, that is A, B, C, D. That is absolutely fine. Delta star A0. A on 0 is A. Null transition to B and D. So B, D will automatically come. We consume 0. In state A, we consume 0. Therefore, answer is A. After consuming 0, answer is A. Then there are 2 null transitions. So B and D will automatically come. A, B, D automatically will come. The second option, we don't consume 0. So A to null, B. So far 0 not used. B to C. Now we are using 0. So answer will be C. Answer will also be the state C. Alternatively, we don't use 0 and go to D. Now we are using 0 and going to E. Therefore, E will be included. So it is A, B, C, D, E, all states. It is A, B, C, D, all states. Similarly, find out delta star A1. Find out delta star A1. Find out delta star A1. Okay, A1. So one of the answers is D, because we don't use 1. Make transition. Zuzar is saying B, D, E. Zuzar, B won't come in the answer. DE will be there, but not BDE, only DE. The answer is only DE. The reason is, see, A to B, we are using null transition. So 1 is not used. 1 is not used. 1 is used only when we go to state E. A to B on null and then B to E on 1. So answer will be E, but won't be B, because it is on null. A to B on null. It is on not on 1. And we are computing delta star A1. B won't be there. So it is DE, ABCD and DE, that is delta star A0, A1. Next compute delta star B0 and B1. B0 and B1. I think that is a straightforward one. B0 answer is C and B1 answer is E. So that is C and E. B0 is C, B1 is E. There is no complex calculation because we don't have null transitions. No complexity involved. Simple. Similarly, C, again no complexity involved. Straightforward. C, let's look at C. On 0 not defined. C on 1 answer is B. No null transitions. After this, that B, etc. So answer is phi and B. Similarly, taking D. Again, beyond that D, no null transitions are there. So D0 is E, D1 is D. Simple. And again, E, the calculation is simple, phi. So this is my NFA, transition table for the NFA. My initial state is A. And from A, using only null transition, I can't go to any accepting state. So no change in the accepting state. It is like this, very simple. My initial state remains A. From the initial state A, using only null transitions, we can't reach any accepting state. So no change in the set of accepting states between Nfnl and NFA. So E was the only accepting state in Nfnl, remains only accepting state in NFA. E. In the previous example, what happened? Using null transitions, from the initial state A, we can reach the accepting state D. A to null B, B to null D. So we added A as an accepting state. A was added in as an accepting state. Whereas in the second case, we can't reach to any accepting state from state A using only null transitions. We can reach B and D, but they are not accepting states. Therefore, only accepting state in equivalent NFA is the state E. You can see here. Now, same number of states. So it was ABCD, 5 states in Nfnl, 5 states in NFA, ABCD, E. Only accepting states is E. The initial state is A that we have done. Now those transitions, A on 0 is ABCD and on 1 is DE. So A on 0, you will see transitions from A to every state. A on 0 is itself, to B, to C, to D and to E. A on 0 is A, B, C, D, E. Transitions defined from state A to every other state. also itself. So A10 is A itself, A10B, A10C, the upper link, A10 is E, A10 is D. And A11, it is DE. So A11, the answer is D as well as E. So apart from 0, we can make a transition to D11. So it is 0, 1. A to D, 0, 1. Similarly, A to E, it is 0, 1. From A, we can reach E on 1 also. So A, E on 1 also. That becomes 0, 1. Similarly, remaining transitions. Already we have defined accepting state. We have defined the initial state, and this is my equivalent NFA for the given Nfnl. For this Nfnl, we constructed this transition table. Actually, last two columns are based on our definition of delta star. However, we have directly calculated using the same concept. We have directly calculated, and because we calculated directly, we are not using the content of the second column, third column, fourth column. Last two columns, they are important. This is actually my NFA. We can specify the initial state. We can specify E to be the accepting state. That is also fine. We can just put last two columns. Alternatively, a better approach is to plot the diagram. More visual. Use better visual effect. The state transition diagram. This is my equivalent NFA. As far as possible, plot the state transition diagram from the examination perspective. It is fine with me, but other person may like to see the diagram. Unnecessarily, there is a risk of losing some marks. If I'm there, that's fine, 100%. There's no change. Okay, so this was example number 2, Nfnl to NFA conversion. Is that fine? Is this clear? So if, okay, Keval, Devansh, Munaf, Abhi. So if these people in their LOR, if they are taking LOR from me, if they write that they were participating in the class, that's fine. Remaining students, please don't overclaim. If you're not participating, it's your cloth, doesn't matter to us. But don't make us tell lie. Don't show that you are so much actively participating, and other students would not have understood. Even I could not have conducted the class smoothly because had you not been there in the class. As of now, it is null and void. You are there or not there, there's no difference. You are not seeing any. Your presence is being not seen anywhere. Don't tell lie. At least don't tell lie in my letter. Doesn't matter to me. Okay, next example. I won't tell lie. That's all. Because of your inactiveness, I won't tell lie. That's it. Otherwise, it doesn't matter to me. So this was NFA for given NFA null. Once more, for the sake of practice, I think we are converting this NFA to DFA. Again, as far as theorem 4.2 is concerned, that is over. That is using theorem 4.2, we have constructed equivalent NFA, this one, for the given NFA null. For further practice, the subset construction algorithm, we are converting this NFA to DFA, that is deterministic finite automata. Only when we write FA, by default it is DFA, deterministic finite automata. So the subset construction algorithm, same titles, S, delta S0, delta S1, we copy the first row, leftmost column, and the rightmost two columns. So it is A, B, C, D, D, A, B, C, D, D, A, B, C, D, D. That is my row number 1. Converting NFA to DFA. A, B, C, D, D, 3 subsets, 3 labels, 1, 2, 3 respectively. Then we move to 2. That is A, B, C, D, E. So A, B, C, D on 0 and 1. Only last 2 columns, looking at last 2 columns. When we take union, the second last column union, it is A, B, C, D, very simple. And the union of the last column, A, B, C, D we are taking. So our current subset is A, B, C, D. So delta A0 union delta B0 union delta C0 union delta D0 union delta E0. So that's the second last column. So it's union of everything. It is ABCD. In the rightmost column, answer is BDE. Answer is BDE. So that becomes my next row. ABCD is ABCD and BDE. ABCD is label 2. To the subset D, we have given label 3. A new subset BD label is 4. The label 4. So we continue. Label 3, DE. Label 3, DE. Label 3, DE. So answer is E and D. E and E union we are taking. So it is E union phi. Answer is E. D union phi. Answer is D. So E and D. E and D. New subsets, new labels, respectively 5 and 6. We have worked till 3. Taking next 4. 4 is BD. 4 is BD. And here BD. D, DE. So it is C, E phi. Answer is CE. In ED phi, answer is DE. So CE, DE. Answer is C, DE. The union, it is C and D. C is not encountered previously. So label 7. D is existing as label 3. So that is label 3. Up to 4 we have worked out. Next is 5. Next is 5. In 5 is label E. Let's see. 5, that is label E. Label E. So that is 5, 5. E, 0 and 1, that is 5, 5. And 5 is again a new subset, therefore new label. E, that is 5, 5. We have used label up to 7. So this is label 8. We have different transitions till 5. We take up 6 next, and that is D. That is 6 is D. So we take up D. Let's see D. D. Answer is ED. Answer is ED. Number 6. E. Answer is ED. And E and D have been previously encountered as labels 5 and 6 respectively. So those are 5 and 6. You have defined up to 6. My 7 is CE. So let us go to CE. CE. Union is phi and B. Last two columns we are saying. So it is phi union phi, answer phi. And B union phi, answer is B. So it is phi B. Phi B. That is my phi is label 8. B is a new subset, new label, that is 9. So you have defined up to 7. 8th is my phi. Blindly it is phi, phi, phi. Phi is blindly phi, phi, phi. We must have a label corresponding to phi. Please understand that. Usual mistake is we ignore phi. That is a dead state, can't be ignored. So that is 8. 9 is B. 9 is B. Let's go to B. Should be simple. B is C and E. B is C and E. B is C and E. C is again a new subset. So that is label 10. E present as label 5. We have defined up to 9. So 10th we take C. Let's see C. C is phi and B. C is phi and B. C is phi and B. Phi has appeared at 8. B has appeared at 9. And no more reachable state from 1. So we don't consider more subsets. No more subsets. So we have 10 states. Now we have 10 states in corresponding DFA. So those, I don't know. Yeah, those are 10 states. Accepting state was E. Accepting state, that was E. Only accepting state is E. So look at the combination in which E is present. The E is present in 2, 3, it is present in 4, it is present in 5, it is present in 7. That's it. So those are my accepting states: 2, 3, 4, 5, 7. That's all. So those are accepting states. So you'll find double circles there. You'll find double circles there. There are 10 states. My initial is state number 1, and then based on this we have defined the transitions. 1 is 2 and 3 on 0. So 1 is from label 1, 0, 1. It is 2, 3. They happen to be accepting states, and again based on this table the remaining transitions. This is my equivalent DFA corresponding to my input Nfnl. See, look at the structure of this Nfnl. Look at the structure of this Nfnl. This one actually. 0 star, 0, 1 star, 1 union, 0 star, 1 star, 0. And how complicated is corresponding DFA? How complicated is corresponding DFA? That is the advantage of non-determinism in the case of finite automata. Number of states drastically reduces. Even in the case of NFA, number of states are much lesser. Number of states drastically reduces. The structure closely matches the RE. The structure closely matches the RE. Otherwise, we are not. There is no another advantage like more language is accepted. Same number of language accepted. Structure is simple, lesser states, less memory, and structure of NFA closely matches the RE. The process of constructing NFA for Nfnl, for that matter, it is much simpler than constructing the corresponding deterministic finite automata. This was the case. So with that, we completed theorem 4.2's application, converting Nfnl to NFA. We'll continue in the next lecture from Klein's theorem, and then later on we'll discuss about this theorem 4.2, constructing NFA from Nfnl, that is for theorem 4.2. We'll see which sequence to follow. Probably we'll discuss Klein's theorem in the tomorrow's lecture. Okay, fine. We stop here.